Virtually every country in East and Southern Africa is a nation of mourners.
Large parts of Africa, a continent home to approximately 800 million people, or around 13% of the world's population, have a pressing need to improve their inadequate medical and hygienic environments. Within the 53 countries in sub-Saharan Africa, there is an epidemic that is bringing destruction to the humanity of this enormous continent. There are 40 million people in Africa infected with the AIDS virus. Most will die from this devastating disease. Many children will never know what it's like to live in a family environment, if they live at all. As scientists, we all have an interest in the impact of our science. For some, there is only an interest in the publication of a discovery. For others, the driving force is how that discovery impacts society. The field of cytometry started with people like Moldavin and Gocke, two very different individuals working in totally different fields, one in biology and the other in mining engineering. For analytical cytometry to become a field, there had to be a meshing of biological need with a technical or engineering capability. How did this all begin? After the Second World War, the impact of the atomic age was a driving force for many technological developments.
When I first went to Los Alamos and went to work under Maurer Vandilla, our primary interest was in monitoring the fallout from atmospheric nuclear weapons testing.
There were many scientists who were engaged in the study of the effect of radiation exposure. However, with the advent of the 1963 Nuclear Atmospheric Test Ban Treaty, there was less need to deal with radiation research.
Marv and I then became interested in exploring, at first, a Coulter counter, which is a device that's commonly used even now in hospitals to analyze blood samples, giving a blood cell count and measuring the size of the blood cells so that you can determine if an anemia is present. We had a pathologist in our group who was using that device to analyze blood, and he would adjust the aperture current and some other characteristics of the machine in such a way that he could cause a small subpopulation of the red blood cell distribution to move away from the main distribution of red blood cells. And the pathologist thought that that represented immature red cells that had just been produced. Well, Marv and I did not believe that that was the case, and we set out to try to convince him that he was incorrectly using the device, and we were not successful in doing that. It occurred to me that if I could just pick out this, what was thought to be abnormal population, just physically isolate those cells, run them back through the Coulter counter, get the same distribution, it would demonstrate that it was an artifact, that he was misusing the machine. Then I saw a paper by Dick Sweet, who at that time was at Stanford Research Institute, working on I believe it was a Navy project, maybe an Air Force project, to develop an ink writing oscillograph.
And the goal of this work was to write with small droplets of ink that were generated and deflected by the methods that eventually became the same methods used in the cell sorter.
By combining Wallace Coulter's cell sorter with Dick Sweet's ink writing oscillograph, Fulwyler created a new technology for cell biologists.
Before we did any work, I wrote it up, just a paper describing the idea, and passed it around to, I believe, about 8 different scientists, asking them to read it and give me their opinion as to whether or not it was a feasible idea, and they thought it could be made to work. The majority of that group of 8 said no, that they didn't think it would work. But under the encouragement of my boss, Wright Langham and Marv Vandilla, I went ahead and tried it. There's a piezoelectric crystal mounted in this part of the system. It's 1 inch in diameter and 1/2 inch thick. The energy, the vibrational energy produced by the crystal is coupled into an aluminum rod here, which rests right up against the crystal, and from the aluminum rod into this plastic horn. And so this shape of an acoustic horn is like a transformer, and it increases the amplitude of the motion, even though a smaller amount of mass is moving. Within this portion, the end of the plastic rod is in direct contact with the liquid. Coming out of the platinum disc then, through a small drilled orifice of about 60 microns, you have a liquid jet which travels down for perhaps a centimeter or so, and then, because of the action of the piezoelectric vibration, it breaks into droplets. When we were first at Los Alamos, we came up with this system, and then Marv took it on to develop the fluorescence sensing and lasers and so on.
We set out to see whether we could adapt the fluorescence staining of cells that had been developed from microscopy to this flow system technique where we could flow them by and measure them thousands per second. And so we decided to move on from the Coulter principle, which had been the initiation of all of this, to optical measurements of cells.
Even though we were in a biological group at Los Alamos, we had a hard time getting the biologists to really accept the idea of quantifying cell populations. The first biological group who could clearly see the uses of the method were the Herzenbergs in Stanford, who could see the application of fluorescence sensing and the use of antibodies in the characterization of immunological properties of cells and of surface properties of cells. So those were the first two heavy uses, DNA analysis and immunological staining.
At about the same time as Fulwyler, Van Diller, and Herzenberg were working in the United States, Goerde and colleagues were expanding microscope-based cytometers and were the first to publish fluorescence-based analysis in flow cytometry, as well as the distinction of building the first commercial flow cytometer to use fluorescence detection. Cytometry has changed a great deal since Mack Fulwyler invented the cell sorter in 1965. Since that first instrument, over 30,000 sorters and analyzers have made their way into laboratories around the world. The impact on science has been enormous. The African continent is under a tremendous challenge. Cytometry has become a tool of necessity for the therapeutic monitoring of the millions of AIDS patients whose very lives depend upon gaining access to drugs whose efficacy must be monitored several times each year. Reducing the cost of these tests, increasing the accuracy, making the cytometric technologies more accessible are not options, they are a necessity.
If you go to Nairobi, you have now almost 1 million orphans at the street, alone in Nairobi, HIV orphans. The countries, the governments gave up. They have no answer what to do with them.
Mack Fulwyler started the process with this sorting chamber. That process has been matured over the past 40 years by many scientists around the world. Every member of the International Society for Analytical Cytology can claim a small amount of credit for the impact of cytometry on human health and welfare. Many of our members are intimately involved in working with AIDS or with technologies that could change the paradigm for those infected with HIV in Africa. Whether you work in clinical or in research aspects of cytometry, the origin is the same. Clinical applications are frequently dependent upon the innovations of basic science. Innovation is often a process that demands risk. Mack Fulwyler was a great innovator for cytometry. He invented the technology that each of us take for granted on a daily basis.
I think it's an anomaly that it happened at Los Alamos. There was no stated need for a cell sorter. Nobody expressed the idea that that was necessary or important to biology. There was no process by which a proposal was written and submitted to a review board for consideration. It was a decision made by my boss, the boss of our group, Wright Langham, based on his opinion, substantiated by a few close advisors, that it was a worthwhile project to pursue.